To get the max productivity and performance out of your cutting tools, you need to have really good, secure gripping. Hello, my name is Alan Miller. I'm the Senior Engineering Manager at BIG DAISHOWA here in Chicago. Tool holder clamping pressure just kind of gives you an idea how much force that tool holder is putting on that cutting tool. The higher the gripping force, the more secure and stable that tool is going to hang onto that cutter, and the faster and harder you're going to be able to push it. Often the most common issue that arises with poor gripping strength is just tool pullout. With the flutes of the tool trying to engage in the material, it tends to try to pull the tool away from the spindle. And if you don't have enough gripping strength, that tool is going to extend out a little bit. What that will do is it may break the tool, and you'll know right away, but it may not. And it may just extend the length and change your geometry of your final part, and you won't really know until the end. So having that secure and safe gives you that extra confidence that that part's going to finish correctly. So there's several different types of tool holders. We'll start with just the milling type tool holders that goes all the way back to the Weldon style side lock holders. Still in use to this day, still have an appropriate place, but they start with a tapered screw that goes into a very controlled taper slot on the cutting tool. Locates on those tapered angles, so it gives you good axial location with that physical stop of a screw. So that was the oldest technology. As things progressed, we got into things like the shrink fit holders that just use physical properties of steel. When you heat it up, it will grow and expand and make a hole bigger. Drop your cutting tool in there, and as it cools, it will retract and grab onto that tool. So those get a little more sensitive to that because the tolerance of the bore and the tolerance of the shank can combine. You have to have the hole big enough to get the biggest cutting tool shank in there when it's heated, but it's also got to be small enough that it will still grab onto the smallest tolerance cutting tool shank that can go in there. So it's a delicate balancing act with shrink. To flip that on the other side, the next technology was more of the hydraulic program. So it still uses that same interference fit between metals, but instead of growing to shrink back down, hydraulic chucks start slightly bigger so you can get the cutting tool in there, and then use a screw with a piston to drive a fluid to compress an inner core to grab onto that tool. These are a little more adjustable than the shrink. You have two screws in these. So during assembly, they have a secondary screw that they can control how much pressure is being developed by that main clamping screw and really control that size. But in the end, it still has a very slight amount of actual physical range to it. So the gripping strengths are limited. The next step up from there gets into what we call the mechanical milling chucks. These are much larger diameter mechanical chucks that have very thick wall body cores and a series of needle bearings that are in the nut. So as you tighten the nut, these needles climb a slight incline and really crush down that inner core. So because of the thickness and the amount of potential energy stored in that system is much higher than shrink or hydraulic, we get about double the gripping strength that you get with those standard type products. So we can go from the physical screw to physical properties of steel into fluid driven into mechanically actuated style systems, at least with the things when we get outside of the collet chuck world. Collet chucks still exist, and they're plentiful and used in a lot of applications. So the collet chuck systems all work by generally trying to push a tapered collet into a tapered hole. So angles vary greatly by design, but that also changes the flexibility. So you get to larger taper angles on the collets, that the clamping ranges are more. As you get tighter and tighter, they can't really give you much radial collapse without a lot of axial range. As you get to those narrower collets though, the forces generated are greater on the cutting tool shank than as you get further out. They're pointed more up and out. So you can get into quite a variety of collet chuck series that have different properties for different applications. As far as over-tightening things, as a company, we're trying to stop that as much as we can because it can cause issues in performance. With older technology, the amount of force needed to tighten that nut may be a lot higher then than it is now. So it's very easy for an operator to get in his head how much torque he's going to need to apply to a collet chuck. Or if you take a high-performance version like we do that has a bearing in the nut, the actual required force is much less because of that the bearing multiplying the force going into that clamp. When you do that, you just distort the bore, the nut, the collet, and everything gets less stable, more probable to pull out, worse run out, and worse conditions overall. And of course, bad run out leads to either short tool life, if it's a drill or a singular or a similar axial style tool. You'll see poor finish or odd tool wear if it's a mill where you've got multiple teeth engaging at different times at different depths of cut. So sticking with the vendor specified tightening torque will go a long way for better tool life and better part quality. If you really see big spikes or movements in where that tool is, you're almost certainly over-tightening it because you're just distorting the thing in different places every time. So what you're looking for is, if you're getting the right amount of torque, you're going to get a lot of consistency. It's going to be the same run out, the same place every time. So besides that repeatability, the other things to look for is to do visual inspections of all the clamping bores. From every type of tool holder, you can look and see, the distortions, marks, tool breakage at some point. You're just making sure that there's no real big lumps or gouges or anything. As far as tool holder assembly best practices, I always like to start with cleanliness first, no matter what type of tool shank. Once you get oils or dirt or lint or anything in between these surfaces, all the work that you're doing to control run out is out the window. It doesn't take very much, a couple of micron speck weight at the back that can propagate out to tenths further out. So you can put in all the work you want on trying to control run out and precision, but if your operators aren't being extremely careful when they're cleaning and assembling these things, it may be for nothing. So always wipe down every tool, always fully disassemble every tool that you're taking apart and putting back together. Take the collets out of the nuts, take the whole tool apart, make sure everything's clean and dry before reassembling. The second one is always to make sure that the thing you're gripping is all the way through the ground portion of that tool holder. So whether that's a side lock end mill holder or a shrink or a hydraulic or anything, the worst thing you can do for any of these tools is to short a shank. And when I say that, not having the full ground length of the cutting tool sticking all the way through the ground area that the tool holder is gripping on. So if you look at the back of say a collet chuck, you'll see they're deeply recessed for the smaller tools. So it doesn't have to be real long, but it's got to just get through that ground section. Anytime you short those or get it partially through those ground sections, you're really compromising your gripping strength, you're increasing run out, and you're probably going to damage that component over time. So assuming that you're clean and you're going to be gripping on a full surface, it comes down to kind of that torque management and using the right tools and the right process. When we talk about tightening collet chucks, we want to make sure that we're using long, smooth pulls when we're tightening. You don't want to get to a point where you're getting stuck and then really starting to jerk on it, because you're not putting a consistent force on there. You always want to make long, smooth pulls until it stops. If you're using analog wrenches, all of our wrenches have different handle lengths depending on how much torque you're supposed to be on there, so you shouldn't have to get really aggressive with ours. Versus if you've got a torque limiting wrench or one of our digital wrenches or torque fit style units, they'll give you an actual audible beep or feedback on when you're at that proper tightening torque. So clamping pressure is important because it's physically keeping that tool in the tool holder while cutting. So to get the highest possible performance, the maximum metal removal rates, You want to make sure that that tool is held very, very strongly and in the right spot.